Hello everyone, my name is Prithvish and I am an MSc graduate from the Delft University of Technology, and today I'll be presenting our work which I pursued as a part of my master thesis continuation at UDelft and IMEC. Without further ado, let's move on to the slides. The paper that I'll be presenting today titled SENSIM, an event-driven parallel simulator for multi-core neuromorphic systems, which primarily describes the design of a simulator that could be used by the research community working on scaling up their existing neuromorphic systems. The co-authors of the paper include researchers, majorly from the Inter-University Microelectronics Center and professors at University of Twente and Delft University of Technology. As a part of today's talk, I'll begin by highlighting the global importance of the project, followed by a brief introduction to neuromorphic computing. Next, I'll discuss SENECA, a scalable neuromorphic computing architecture, the research work conducted prior to the development of SENSIM. Following that, I'll delve into the motivation behind SENSIM, detailing its model and GUI. Next, I'll showcase some experiments conducted on the platform and the results extracted from them. I'll wrap up today's talk by sharing future research prospects with SENECA and SENSIM. In the year 2022, the International Energy Agency released a Global Energy Crisis report highlighting clear trends in rising energy consumption post-pandemic. While the report was alarming, it also underscores the importance of energy as a critical parameter. The increase in the need of computation across various market segments such as industrial automation, automotive industry, smart cities, and more have led to a significant rise of energy consumption on the computational side. As researchers, it is our responsibility to focus on reducing the energy footprint of these computational devices without affecting the efficacy of the system. Artificial intelligence has emerged as a prominent area of research in the last few decades, making DNNs as the primary workload. Researchers in the field pointed out that the energy consumption of DNNs when executed on a normal GPU is significantly higher and rather wasteful as compared to SNNs, the neural networks developed by extracting temporal and spatial sparsity. Meanwhile, on the other hand, researchers that have been developing neuron models to understand how the brain computes data and performs cognitive tasks also pointed out that the brain would process these cognitive tasks in a far more energy efficient manner as compared to existing computational devices. Drawing conclusions from these two fields of research, researchers and computer architects came up with designs that would resemble the brain to best accommodate artificial intelligence data. These designs were rather more memory-centric and would reduce the communication latency between memory and compute. These designs majorly include in-memory and near-memory computing architectures. In the recent years, a scalable neuromorphic computing architecture also emerged out of IMEC, focusing on reducing the energy consumption to best cater the evolving needs of artificial intelligence. The architecture revolves around having a scalable data memory which could be expanded in MBs depending upon the memory technology available, accompanied by a variable number of neural processing elements positioned close to the memory, thus forming a near-memory computing architecture. To manage the energy-efficient data flow within the core, a low-power RISC-V Apex controller was further added to the architecture. To store instructions close to the controller, a small instruction memory was further required. An Axon message interface bus to transmit events from the external circuitry to the processing core was further added to the architecture. A shared memory prefetch unit, a highly optimized bus responsible for prefetching data and making it readily available from the external memory without affecting the data processing latency, was further added to the processing cores. Loop buffers responsible for buffering data while processing it on the neural processing elements, and event capture units responsible for buffering data before transmitting it to the next possible processing core was further added to the architecture. To make the architecture scalable, the processing cores, also called as the neurosynaptic cores, were further replicated and scaled up to 64 and beyond. Over the last 2 years, SENECA architecture has evolved to best accommodate large-scale spiking neural networks by adding shared memory blocks to the existing architecture. These shared memory blocks are connected by the means of an arbiter to the neurosynaptic core. As the architecture continues to evolve, there arises the need to test and validate large-scale spiking neural networks on SENECA efficiently. To address the scalability requirement, a simulator was required which could scale and mimic the processing of large-scale spiking neural networks on SENECA. Thus came SENSIM. SENSIM mimics the workings of SENECA on a software platform and produces accurate results, enabling faster design space exploration by providing estimates of time and energy. This facilitates the validation of implementing large-scale spiking neural networks processing on the architecture. Being written in Python, SENSIM offers easy integration with SNNs and DNNs. For accurate modeling, SENSIM would still require temporal events as inputs, which could originate from a DVS camera or artificially be generated from video processing datasets. Additionally, it also requires files such as the technology file detailing the transistor technology used in the architecture, the architecture file reflecting the evolving architecture of SENECA, an application file representing the SNN DNN applications mapped onto the simulator, a mapping file indicating where exactly the neurons from the application would be mapped onto the multiprocessing system. The output thus can be validated by the means of plots in the simulator. While SENSIM mimics SENECA, it also offers the flexibility to model several other neuromorphic chips. SENSIM as a simulator provides the flexibility to modify various aspects of the neurosynaptic core, such as the neuron models, quantization schemes, compression mechanisms, queuing frameworks, layer types, interconnects, SNN and DNN application utilities, and more. SENSIM is modeled in such a way that it provides the user the flexibility to vary the following parameters: energy, timing, architectural, communication, quantization, and platform execution. SENSIM also comes with a visually appealing GUI. The slide features the GUI of SENSIM demonstrating events from a dynamic vision sensor being processed on the simulator, with the output of PilotNet SNN on the right. At present, the simulator GUI provides insights on the processor utilization represented in shades of red, input-output queue utilization in blue, within a multi-core processing system. The slide showcases some of the application outputs captured in SENSIM. The first example showcases two outcomes of PilotNet SNN inferences executed on SENSIM. The second example showcases outcomes of a four-layered MNIST-trained DNN network inference executed on SENSIM. During experimentations, we identified variations in the captured outputs when certain SENSIM parameters were altered. Interspike distortion, a common phenomenon observed in SNNs, was noticed when varying mapping schemes for PilotNet on SENSIM. When varying timing parameters for MNIST-trained DNN network, we observed that in one case, the digit 5 was not classified correctly. These valuable insights enable us to evaluate output accuracy well in advance before deploying these networks on SENECA. Below are some of the architectural and communication parameters that can be adjusted on SENSIM. While these are default values optimized for the execution of the PilotNet SNN framework, they can be adjusted as per user needs. Below are some of the energy and timing unit parameters extracted via low-level experimentations on software such as the Cadence Juice. These parameters vary based on the design and technology node used in the architecture. Here's a comparison of SENSIM with other simulator softwares developed by the neuromorphic research community. Whereas SENSIM stands out in estimating energy, power, and latency for a scalable architecture as compared to others, there's still room for improvement in the software when it comes to evaluating online learning on a chip. Next, I'll present some pivotal experiments conducted on SENSIM and highlight the valuable results gleaned from these experiments. In one of the experiments, we observed that there was an energy reduction of around 8% by increasing the number of NPEs. A similar trend was also observed when estimated latency on the similar architecture. In our spike compression experiments with PilotNet, we found that the compressed sparse column event compression scheme outperformed address event representation, reducing the number of communicated flits and improving the processing time. In an experiment, we varied the number of spike registers for PilotNet and noticed energy improvements. We observed that the energy improvements were noticeable up to 8 spike registers in a neural processing element. However, beyond this point, the energy remained stagnant. For the experiment, we observed that having a shared memory with a bandwidth that supports a transfer rate of 128 bytes per cycle does not introduce any processing delay in the output and performs similar to having the data stored in the local memory. Looking towards the future prospects, addressing the optimal mapping of large-scale spiking neural network requires the development of a mapping tool named SENMAP, tailored to efficiently map them on SENSIM or SENECA. Although SENMAP is developed, it is yet to be formalized in the form of a paper. Furthermore, there are plans to enhance the SENECA cores by expanding them onto a third dimension. The research team also intends to focus on integrating large-scale spiking neural networks and support different neuron models on SENSIM. Collaborations with the external research community is encouraged to further refine the design. For any bugs or queries, feel free and reach out to me on the given email address. For collaborations on additional sub-projects under Seneca, please reach out to my mentors, Amreza and Manolis. Thanks for your time. For any queries, feel free and reach out to us.